Hello Year 11. I'm going to go through the idea of a simple DC motor. So DC, direct current, so it's when you've got it connected to a normal cell and the current's flowing in one direction. You need to use the ideas of the motor effect that you've already met and the idea of Fleming's left-hand rule. So you need those two ideas combined together to see how we can make a motor spin. Right, let's look at what makes up a motor. In order to make up a motor, you need to have a cell, and this represents a coil of wire. So you will have a cell connected to, going into one of the pieces of wire. The wire wraps round several times and then comes out the other end and connects to the other end of the cell. That coil of wire will be put inside a magnetic field, so between a north and south pole. It doesn't matter which way round the north and south are or which way round the cell is connected. The only way that will affect it is which way the coil spins. So the first thing you need to do is work out which way the current is flowing. So I'm going to draw that on. We know that current flows from positive to negative. So the current is going to flow through this wire up here, and then this wire wraps around this way. So the current's going to come up here, along the top, down this side, back out of this wire, and then that's going to flow back through to the negative to complete our circuit. We now need to put Fleming's left-hand rule back into it, and we need to work out which way the coil is going to move. Just focus on one side of the coil at a time. You can't do both at once, but I will show you that it works both ways afterwards. So I'm going to focus on this side of the coil. So we know the direction of our current, so align your three fingers for Fleming's left-hand rule. Remember, the second finger is current, so the current is coming towards me. Now my first finger is field, and we know that field goes north to south. So I need to reverse that. So the current is going away from you towards me. The field is going from north to south, and that shows me that the force is acting down on that side of the coil. So that means that side of the coil will move down. We know that the opposite side will do the reverse, but I'm just going to show you that so you know you don't need to do both sides. So on this side, the current is going away from me. The field is still going from north to south. So I have the current lined up, I have the field lined up, and it's showing that the force is now up. So this side of the coil will move up. So now we can look at what happens to the coil. We know that this side is going down and this side is going up. So the coil is going to turn like this. When it gets to the top, momentum will keep it going until it ends up this way round. Now we're looking at the other side of the coil. So the current is still attached to the same side, so it's coming up this way and back down that way. What that means is our positive side is now over here next to the North Pole. So our current is flowing up that way, our field is going across, the force is going down. So that means this side's now going down. And what that's going to happen is that's going to keep reversing. And our coil is keep flip-flopping over. And it's not going to spin, which is what we actually want. So we need to make an adjustment. Rather than having the contact points here fixed, we make what are called brushes. Now this isn't an accurate representation, but it will show you how it works, and then you can apply it to the diagram. The brushes touch our contacts, but they're not attached to them. So they're free to move. So this time, we start the same with Fleming's left-hand rule. The current is coming up towards me, the field's going that way, so this side's going to go down, and we know the other side does the opposite. So this side's going to go down, and it's going to spin. Now, we lose contact, but momentum will keep it going until it flips over. And when it flips over, they make contact again. But what I've got written on here is now wrong. This was what we had before. The wires haven't twisted this time. So here's my positive still attached to this side. So let's change it. We're now coming up this side and down that side. It's coming up, round and down. So let's have a look. Now This side has got the current coming up exactly the same as it did in the beginning. We've still got it going down. So this side's going down, which means the other side's going up. Over it goes. We've still got it in the same direction now, so it's going to keep going down and keep going down. So as a result, it will keep flipping over. Now, if this was set up properly, they would stay in contact every single time because they're in fixed position, which means it will just keep spinning round. Beyond that, all you need to know is what happens if you reverse the direction of the current by connecting the cell the other way around or changing the magnetic field direction. If you reverse the current, it will turn the opposite direction. If you reverse the magnetic field, it will turn in the opposite direction. And therefore, if you reverse both of them, it will go back to where it was because the current will reverse it and the magnetic field would reverse it again, and we'd end up with exactly the same situation.